Hello, and welcome to the first video here in our module. So we're going to start Unit 9 over this break so that we can be able to come back and have more time to review before the AP exam. So there's going to be 4 parts to this module, so 9.1, 9.2, 9.3, and 9.4. In this video, I'm just going to do 9.1, and the subject of this video is going to be entropy. So this should be a familiar diagram to you. So this is our energy diagram of a chemical reaction. So we have our energy level of our reactants, the energy level of our products, and the difference between the reactants and the products, that's going to be the change in energy or enthalpy during our reaction. But in this chapter, we're going to talk about how this, okay, and this are related. We haven't really put 2 and 2 together, so that is what we are going to be doing in this unit, okay? So in the green, that is the domain of thermodynamics. It shows us the change of energy, also where we start and where we end, and in between, that has to do with kinetics. So remember what it takes to get all the way up here to the top of our peak. That's our activation energy. So in this unit, we need to be focusing on using the term thermodynamically favorable as opposed to spontaneous. Okay, so get away from saying spontaneous and say thermodynamically favorable. What this means is the process, a chemical reaction, or perhaps even a physical reaction, will occur without the help of outside intervention, okay? So it can be fast, it can be slow, it can depend on the temperature, but for something to be thermodynamically favorable, all that means is that it will be able to occur without outside intervention. Okay, so with thermodynamics, we talked about how the process starts somewhere and then ends somewhere, but we also have to consider what happens in between getting to that activation energy. Okay, so here's the deal. When we talk about something that is thermodynamically favorable, it is something that will proceed towards a certain state. Now, a chemical reaction can proceed towards a state of less entropy or more entropy. But the entropy, how do we define that? That is going to be kind of like the randomness of the universe. Okay, so we'll define that in a moment, but we need to know that, yes, a lot of exothermic reactions, because they release energy, are spontaneous or thermodynamically favorable. However, not all of them are. Okay, so we have to consider not just the enthalpy, but also the entropy. Okay, so entropy is a thermodynamic function. It is considered to be the disorder or the randomness of a system, the system being like our materials, right? So it's the molecular randomness. So it's the dispersal of everything within our system. So basically we need to ask ourselves, with the system that we have, how many arrangements are available? The more arrangements you have possible, the more disorder the system will have. Okay, so the symbol that we're going to use for entropy is S. So consider that what we have over here, right? So think about possible arrangements as microstates. So we have a vessel, and the vessel has 4 molecules. It's not just the vessel that we need to be concerned about, but look at how we have 2 sides, right? So how can these 4 molecules be arranged? Well, if we look here, we could have all 4 in one or the other. We have 3 in one and then 1 in the other side, okay, like we do there, or we can have 2 in each side. but which of these is going to be most likely to occur? All right. So we need to figure out how many of these microstates we can achieve. So if we look here, we have 1 microstate for this arrangement. We have 4 for this arrangement of 3 on the left and 1 on the right. We have 6 where there's 2 on each side, right? If we consider each of these as individuals. And then we have 4 of 3 on the right and 1 on the left. And then we have 1 of everything on the right. Okay, now check this out. So we have the system of dice, right? When you roll 2 dice, you're playing a board game or something like that. What number do you think is most likely to come up? Well, the one that is most likely to come up is 7, because look, we have 1, 2, 3, 4, 5, 6 possible dice combinations here that they can come up and give us a 7. So about 1 out of every 6 rolls of double dice will give us 7. Whereas as you get farther away from this middle here, it becomes less and less likely until you get down to a 1 and 1 or 6 and 6, then there's only 1 probability of that. Okay, so now what are some things that can increase entropy? So going from a lower entropy to a higher entropy, phase changes. So if we go from a solid to a liquid, or from a liquid to a gas, or from a solid to a gas, we're increasing entropy. So think about it this way. The solid, they're going to be closer together, they're going to be in fixed positions, as opposed to a gas where they're moving around pretty freely. So the entropy of the gas is going to be naturally higher than of a solid or even of a liquid. Okay. Now, what about volume change? So if we go from a smaller volume to a larger volume, we increase the entropy too. So basically giving your stuff more room to move around, more possible arrangements, that gives us more entropy. The number of moles of a gas, well, if we have less moles, and then we go to a state where we have more moles. So think of any chemical reaction, however many moles you have on the left and however many moles you have on the right. If you have more on the right, that means that you have higher entropy as a result of that reaction, of having more stuff, more possible arrangements than what you had before. Okay, the dispersion of energy, if we go from a lower temperature to a higher temperature, again, think about it this way, as something heats up, the molecules are moving around faster and there's more dispersion of possible velocities of your particles, okay? So the distribution is wider. So think of it this way, okay? Everything is within here at 100K, but now look at 1000K. It's much more spread out, much more possibilities in terms of velocities. Okay, so now at the end of this section, I want you to just answer these questions. This will be the actual first question in your Google form. So for practice number 1, try to predict the sign of entropy change for each of the following processes. So if you go solid sugar is added to water to form a solution, that's A. Iodine vapor condenses on a cold surface to form crystals. That is the second one. So again, entropy change, if it's positive, that means that the system is increasing in like kind of disorderedness or in the disorderedness or the randomness. But if it's negative, that means that it is going down, okay? So think about all the previous slides and answer these questions. So is this positive or negative? Is this positive or negative? You can also just say increase or decrease in energy. Oh, I'm sorry, not energy, entropy. And then for practice number 2, for each of the following pairs, choose a substance with a higher positional entropy per mole at a given temperature. So solid carbon dioxide to gaseous carbon dioxide, or nitrogen gas at 1 atm, or nitrogen gas at 1 times 10 to the negative 2 atms. So which of these is going to have the greater entropy? Which of these is going to have the greater entropy? All right, so answer those in the Google form, and that is all for this section.